Hi, everyone. This is David Greenberg with episode 25 of our machine learning seminar. Uh, we're covering fluid dynamics today and maybe appropriate for the extremely weird weather we've been having in Hamburg the past few days, snow falling from a sunny sky. This is a really interesting paper I've been excited about for a while and wanted to present. It combines clever machine learning, careful attention to uh, physical insight, which gets used in the machine learning approach, and a nice attention also to how the method is going to be used and how it can generalize to new scenarios, how it can deal with other constraints of its actual application that we'll get into. And this is a paper that came out very recently from a group in Bonn and was accepted to the International Conference on Learning Representations this year.
Uh,
So
Sorry, very quickly. This is version 3, I think. The original first version came out in June last year.
thanks, Marcel. Yes, it has been out and it's been on our radar for a while. I think comparing to that version, I think we've seen more comparisons with baselines and some other ways it's been improved. I'm actually going to talk a little bit about that and show the reviews at the end of the presentation if there's time. So um, what we're about today is solving the incompressible Navier Stokes equation. So describing how pressure and velocity of a fluid evolve together over time. Incompressible is expressed in this first equation, that the divergence of the velocity field is zero at every point. Uh, what that means essentially is that the density of a single fluid parcel doesn't change over time. And then the bottom equation is just basically conservation of momentum. We're saying the change in the velocity should be times density should be the sum of the forces acting on it. And we've got a force from the pressure gradient. We've got a viscosity force. And we've got other forces that could be gravity or Coriolis forces. But in this paper, they're actually set to zero. So this little F term is gone. So where are variables here? We have our velocity field. We have our density field. We have pressure, which is a scalar at each point, and we have viscosity, which is just a constant. And I don't want to get too much into vector calculus in this presentation, but I think it's worth reviewing just these simple definitions because they'll keep popping up. Whoops, I'm sorry. That is divergence of a vector field, in this case, divergence of the velocity or pressure is simply the um, x derivative of the first component, the y derivative of the y component, and the z derivative of the z component, and you add those up. And when we say that the flow is incompressible, we're saying that the density of a parcel of fluid doesn't change, and that this quantity applied to the velocity field equals zero. And then the other important quantity that comes up here and will come up again later is the Laplacian operator. Here, when we apply this to each element of the velocity field, we're going to get the viscosity force. So this is another important thing. This is just the sum of the non-mixed partial derivatives. So basically, if we're looking at the x velocity and we want the Laplacian, we would say the second derivative of the x velocity in the x direction plus the second derivative of the x velocity in the y direction plus the second derivative in the z direction. So these are basic definitions. This is what we want to solve, and this is what they go about to solve in this paper. Okay, so how would you do it normally? What is the kind of state of the art that they're trying to improve on? The standard approach is numerical integration. So here you look at these equations, you discretize them in time and space, and you'd update the pressure and velocity fields at each time point based on the previous time point, and you just keep applying that over and over. This is typically an expensive but accurate approach. It's also been proposed to speed this up by training a neural network or other machine learning method to imitate the results of a numerical solver. For example, for incompressible Navier Stokes, There's this paper by the Turek group that did this. And this can basically let you get the accuracy of the numerical integrations with a big speed increase. But there's limitations here, right? So you have to generate the training data. You may need a lot of it, and it can be very expensive. So this is generally a limitation. And you always worry about in your application scenario, is the situation going to resemble your training data enough that it's going to work, or have you trained the network for one approach and used it for another? And this is something that this kind of need for supervision data is something that this need for training data is something that these current authors are going to try to overcome with an unsupervised method, which, strange as it sounds, doesn't require data to learn. And third, there's this physics-informed neural networks approach, which we've covered all the way back in episode 1. And here the idea is to train a neural network so that its output actually obeys the differential equation. This allows you to dispense completely with discretizations in space and time. It also means that unlike the first two approaches, you can jump from the initial time point to any time after training, and you don't have to compute all the solutions in between. But the limitation of the physics-informed neural networks approach is that you're completely locked in to your initial and boundary conditions after training. So you can't really generalize to new unseen conditions or to different boundary conditions, such as if you're, in this case, modeling flow through a pipe, if that velocity at the of the inflow changes, you're completely stuck and have to train the network again from scratch. So that's not what we want to do here. Okay, so what exactly do the authors want to do in this paper? We want to solve these incompressible Navier Stokes. We want to do it in 2 dimensions. We want to use Dirichlet boundary conditions, which means at the boundary of our domain, at the edge of our lake or bathtub, or the inflow and outflow of our pipe, we know the velocity of the fluid on the boundary. We want to do it unsupervised, which is to say we're going to use the equations themselves, and we're going to use the fact that we know things like the viscosity constant, the density of the fluid, but we're not going to use any simulations as training data. We can just start from scratch. All the information we need is in the equations themselves. We don't need training data. And finally, we'd like this to work with variable initial and boundary conditions. That is to say, having trained it on some set of initial conditions and boundary conditions, we'd like to be able to apply the trained method to new initial and boundary conditions that weren't seen during training. Okay, so the key physical insight that I think makes this really effective is using the Helmholtz decomposition. What the Helmholtz decomposition does is it decomposes any velocity field. In this case, it's going to be the velocity of our fluid at each point in space at a given time, into 2 parts. And that is a curl-free part and a divergence-free part. So the first part, so we're saying our velocity field V can be expressed as the gradient of a potential Q. So Q is a scalar function, and then if we take its gradient, we get a field again with 3 parts, or 2 parts in the Navier Stokes 2D case. And then the other part is the curl of a vector field. So we're saying that any vector field, or any sufficiently smooth one, there are some mild conditions, any vector field can be expressed as the gradient of some potential plus the curl of some vector field. And why is this useful, right? Well, there are these 2 theorems in vector calculus that are really useful here. First, that if we take the divergence of the second term, we get 0. The divergence of a curl is 0. Likewise, the curl of a gradient is 0, which means this part here has 0 divergence and this has 0 curl. Well, why do we care? Let's go back to our equations we're trying to solve. we want the velocity field to have zero divergence. And we know that the second part, the second term here, has zero divergence. So how can we use this? Well, it's actually used already in a lot of numerical integration-based solvers, right? So even when you're not using machine learning, what you might do is you might look at your equations here, right? Here are your two equations. This is your momentum conservation, and this says, okay, we want the flow to be incompressible. Well, what we can do is we can simply update our velocity field and then decompose it into two parts and keep only the second term, the term which is divergence free, which represents an incompressible flow. And indeed, some numerical solvers simply do this, right? We update using our second equation, the velocity, and then we remove the part which has any divergence, the first term. In order to do this decomposition of the velocity field, these numerical integration approaches typically have to solve a large system of linear equations to obtain these two different terms. So this would be possible as well for this machine learning based approach, right? We could have our machine learning neural network basically take as inputs the velocity field and the pressure field, and then output a new velocity field, do the Helmholtz decomposition, and then remove the part which isn't divergence free. And then we have an incompressible flow. But what the authors, what Wandel and et al. Here do is actually much more clever. Instead of outputting the velocity field from the neural network, they directly output this vector field A, where when we take the curl of A, we get the velocity field. So this means without having to do any of these decompositions, which are expensive computations, we are getting the benefit of the theoretical insight from the Helmholtz decomposition. The neural network is directly outputting a divergence-free velocity field so that the first equation is automatically satisfied. Okay, so this is a basic idea. How are they actually doing this? What is their neural network architecture? They use this unit architecture from Ronneberger et al., which we've seen in a couple different papers already. The idea being that you take a bunch of features as inputs, you do convolutions on them, so you have local interactions, and you're updating each channel based on the nearby elements of the other channels and itself. So you do these convolutions, and then you have these resolution decreasing operations, right? In this case, maximal operations, where you decrease the number of pixels in your space. So they're typically going on something, I think, maybe 200 by 200 or so pixels in their simulations. And you decrease that number and increase the number of channels, then you decrease it again, increase the number of channels, and so on until you get to the bottom. Then as you go back up, you increase the image size, decrease the number of channels. You also have these skip connections where you pass information along the same level of the U until you get back up to the top. And what's going in is this A vector, right? The thing we take the curl of to get the velocity, the pressure, the boundary as an image channel. We'll see some examples of that in a second. The velocity on the boundary, which is from our Dirichlet boundary condition. And then some additional features, which are just other representations of the same information. We get 13 total channels. We push it through our columns, go down the U, go back up the U, and what we get out is a change in our pressure field and a change in A. And after applying these, we get our new pressure and velocity fields. So this is how they do it. So this is the loss function used for training. This should look very familiar if we compare to the loss function used for the physics-informed neural networks in episode 1. Essentially, we're constructing a loss function based on the symbolic pen and paper form of the equations, right? So let's look at the first one. this divergence loss is just divergence of the vector field. So the first equation was the divergence of the vector field should be 0. So we're saying, okay, let's take the sum of square errors if it's not 0. For the second term, the momentum, this equation should be true. So if you actually subtract this from this, you should get 0. And again, we're seeing if that's true or not, right? So if our velocity field and our pressure field are a solution to this second equation, the conservation of momentum, then this term should be 0. And then we have a third term, which just says that our velocity field on the boundary should be equal to the Dirichlet boundary conditions prescription. So we're saying we should have 0 divergence, we should have an incompressible flow, we should conserve momentum, and we should have the correct boundary conditions. And this is basically it. Unlike the pins approach, we don't have to have an error term for the initial conditions because we're starting with the initial conditions as inputs, and then we just have to compute the next time point. Okay, and then we're training this one time step at a time. So we're taking always the previous time steps, velocity and pressure field, and we're seeing if we're getting the right answer on the next time step. For very high Reynolds number, that is for more turbulent flows, they introduce one more term to their objective function, which is a regularization term saying there shouldn't be two extreme pressure gradients in their pressure field. So this is what the training data look like. Basically, and again, we don't need to do simulations to generate training data. So, but instead, what are we inputting? We're inputting boundary conditions and velocities on those boundary conditions. This is all the training data we need. So here's one example, right? We have a flow through a tube around an obstacle. So the boundary is the walls of the tube, that's the top and the bottom, the input and output of the tube, that's left and right, and our obstacle. Now, what about the boundary conditions? Well, you can see we have a positive flow from left to right on the input of the tube and the output of the tube, saying that the velocity of the flow has to be maintained at the rate we specify as it goes in and it goes out. But in between, the flow can do whatever it likes, and it can have all kinds of turbulent eddies and so forth. This is one, and the flow, of course, won't be laminar because there's an object in the way, and this is going to cause changes in the flow and ultimately turbulence at high rates of flow. Another boundary condition they have here, we have the same idea. We have flow through a pipe, but now instead of just a static obstacle, they actually have a rotating cylinder. And the boundary condition is going to be different depending on the rate of rotation. And so basically, if you have a no-slip boundary condition, then depending on how quickly the cylinder rotates, the fluid is going to have to flow past it at a certain velocity to match. And then in the third case, we have this convoluted S-shaped pipe, right, where we have in the lower left the fluid enters our simulation, and then it has to go around the walls, and then it exits in the upper right. So these are basically the scenarios, our boundaries and our boundary conditions in terms of these velocities on the boundary that are used for training. And I'll just summarize the training procedure. What they basically do is they start off with 0 velocity and pressure, and then they, at each time step, they try to calculate the next pressure and velocity fields in such a way that the Navier Stokes equations are satisfied. And then having done that, they use the output after one time step as input, and they do it again. And at each time step, they try to minimize these violations of the boundary conditions and the Navier Stokes equations themselves. After running for a very long time, they then reset the each simulation back to its starting point. Okay, these are the results. In the upper right, you can see is Kármán vortex sheets forming after as the velocity of the flow increases, the Reynolds number is increasing. Um, they are basically increasing the density and decreasing the viscosity, which leads to higher Reynolds numbers. And you begin to see these vortex streets, Kármán vortex streets forming. And this is a qualitatively really nice check. In the bottom row, you see this, I can't remember the name of the effect. It's this, but the idea that you see a pressure difference on the top relative to the bottom because the cylinder is rotating clockwise. And if the cylinder were to rotate counterclockwise, you'd see the pressure difference in the opposite direction. And then finally, they take an airfoil. And even though this wasn't included in the training data, they can see this low pressure region above the airfoil based on its shape, indicating that the airfoil is generating lift. And they compare this to do quantitative evaluation. They compare this to 5-flow, which is a numerical integration package. They find that they're much faster on a CPU and even more, on the GPU, which 5-flow doesn't support, it seems. And they're actually able to match the no divergence condition more tightly than 5-flow does. Although 5-flow, I believe, matches the momentum conservation perfectly. So overall, they're getting pretty much the same or better results, but they are able to do this much more quickly. And they test out two different versions. One of them is this AlphaNet, which I described. In the other case, the output velocity, and the network simply has to learn to output a divergence flow free field. And in this case, you have this additional loss term from the divergence being violated, and you don't need that term in the ANET. Okay. There's one more thing I should say about 5-flow and about this. So I've talked about wanting to solve these equations, which is great, but in the end, we have something really fantastic, which isn't just the ability to solve these equations. We have a differentiable solver, because the entire thing is this neural network. We can easily differentiate the outputs with respect to its inputs, which means we can differentiate the entire fluid dynamics simulation run by our neural network with respect to its boundary conditions, its initial conditions, and so on. 5-flow, the solver they picked for comparison, also supports this. It's a differentiable solver. So why would you want to do this? The cool thing about this is you can solve a lot of optimization and control problems that involve a fluid dynamic simulation. So in this case, they say, all right, we know that when we increase the flow velocity, we're going to generate these, or if we also decrease the viscosity or increase the density, we're going to generate these Kármán vortex streets, these sequence of clockwise and anti-clockwise vortices, which flow downstream from our flow blocking obstacle. And what if we wanted them to come out at a certain rate? Can we adjust the flow in our simulation in order to get the rate of these vortices to be exactly what we want? And it turns out they can do this by gradient-based differentiable optimization, just differentiating through the entire fluid dynamic simulation. So first they define what they want to target, which is they say, look at this white box, right? I want to look at the velocity average in this white box downstream of my obstacle where my vortices are going to pass through. I want to take the frequency spectrum of the velocity over time, and I want this to reach 8. I want a rate of 8 vortices per second as the velocity goes up and down. So they basically define this measure in frequency space. Here you can see the frequency distribution before the optimization, right? So they've trained their network to do the uh, simulations very accurately, but they haven't yet adjusted the speed, right? And you can see the frequency is peaking around 6. They wanted to peak at 8. So then they use the differentiability of the whole model to move this red line to the green line, to move the mean of the this bump in the frequency spectrum to 8. And you can see they do this over iterations and they adjust the flow. This is something you can only do with a differentiable solver. So let me also show their supplementary movie because it's just much too cool to miss out on. And we'll see a few different examples of what they're doing. Start at the beginning, yes. Yes, with 100 by 300 grid. And the amazing thing about this is these are all running basically in real time. So you can actually move the obstacle around with your mouse and or change the flow speed, and it'll actually run at 250 time steps per second. So they can move the obstacle around. You can see the C's. You can change the direction of the flow. The Magnus effect is what I wasn't remembering, right? So as the cylinder rotates one way, this is reflected in the boundary condition, and you get this pressure differential. Now they're changing the direction of the rotation, right? So they went up pretty high in the Reynolds numbers as the flow became more turbulent. They didn't go extremely high to where the flow becomes very chaotic. And the reason they did this is they really wanted to develop a differentiable fluid dynamics simulator, but those derivatives aren't so useful when things become so chaotic. Even if you could calculate them, they'll quickly blow up after a few time steps. So we see high Reynolds numbers, but not what you'd call a fully turbulent flow. And as they go higher, this is where this pressure regularization has to be turned on. This is a shark-shaped obstacle, which again was not at all included in their training data. And they're moving it around, and you can see the vortices it leaves in its wake. I think this is just incredibly cool stuff. All right, so this we've covered. I'm going to skip over. I think that is it. Okay. So then a couple points I'll just make before closing that I think are interesting in a wider context. They have code online. It's in PyTorch. You can download it. You can run it. And then I think this might be really interesting for people who are interested in what the peer review process is like in machine learning. This is ICLR. This is, I'd say, probably one of the top 3 machine learning conferences internationally. It's almost as prestigious as ICML and NeurIPS, or maybe just as much these days. But one way it differs from those conferences is that all the reviews of the accepted and the rejected papers are public. So you can go and look at the reviews of this paper, what the authors responded, and how the program chairs assembled these and came to a decision, in this case, to accept the paper. I think every reviewer voted to accept this paper, which is quite unusual. It's quite a strong paper. So if you're interested in how this works and what kind of and I think this is actually a very difficult field to get papers accepted in some ways, because you may have to convince both the people who are more interested in machine learning that it's interesting, as well as maybe more, let's say, old-fashioned people would prefer more old-fashioned approaches to fluid dynamics and are more skeptical of what machine learning can do. So these papers at the boundary, I think, they have to be quite good, and this one really was. And finally, these guys have since put on archive an extension of this approach to the 3D incompressible Navier Stokes, which also looks really interesting. So this is all I have. Um, maybe we can open up to questions or comments now. I have some discussion points myself, but I hope someone else will chime in. I know some of you guys are working on physics for neural networks. I'd be curious on the perspective there. Yeah, Kubi.
Yeah, so I have a question about how they generalize for this object because they somehow used different objects and then it still worked, right? So how did they again define how the shape of the object is? Is it only in the initial conditions or?
Well, it's the boundary conditions. The initial conditions are really just the velocity and pressure fields, which I think they mainly set to 0 when they generate training data, but then of course after a few time steps of feeding the output back as an input, they have all kinds of things. But the objects appear in the boundaries, right? And then when you actually run this through the neural network, the boundary field gamma is simply this thing on the left, right? So you have a convolutional neural network, the UNet, and it has a bunch of features going in. Some of these features will be things like the different XYZ components of the velocity, and one of them will actually be the boundary map, which is a binary map saying which pixels are inside an object and which are not. So then when the neural network predicts the new value of P or A or V at a pixel, it'll be looking in a region around, and it'll be looking at where the boundaries are. So by having these different objects in different places and these cylinders and these pipes, it learns to basically take into account the location of nearby boundaries in computing the pressure and velocity fields in the next time step. I hope that answers the question.
Yeah, I'm just thinking about also how they so how they did with the training. They also said with the training that they actually just keep predicting and use the output as the new input, right? And then just while keeping to predict it, they always try to optimize. That's also interesting because I thought they would have to start like go back to a certain point to really generalize also.
Eventually they do go back. I think they generate these new random initial conditions with these objects in different places and different flow fields of different flow rates. And then they'll basically start from that initial condition and they'll keep going forward and forward in time. Well, I think in each training batch they'll mix together several initial conditions, and then I think when a condition has been used enough, then the fields start looking like the middle of a realistic simulation. Eventually, then they'll go back to the initial conditions, and I think they'll probably also generate a new boundary for that thing. So I don't think they'll use any one set of boundary conditions infinitely. Yeah. So I think yeah, I think this relates to a couple thoughts I had on this paper. I mean, about the Helmholtz decomposition, it's interesting to think. So they're directly outputting A, so they get a divergence-free field. I'm sorry, we have another question. Björn,
Hello.
hi.
This is another question though. So when we still want to discuss about the previous question.
No, go ahead.
Okay. So their results section, I think, has two competing methods. And when you look at computer vision, then often they have up to like 10 competing methods and show that they're all that the proposed approach is better than all the others. And in the end, this is a new approach here. So I wonder whether you guys think the results section is somewhat sufficient to say that this is actually a better approach than other papers,
Yeah,
or
that's. I
feel
mean, I
like
think part of it is the and I think everyone else should chime in here too. I don't want to just give my opinion, but part of it is that this is a much less mature field than something like computer vision for classification or segmentation,
Mhm.
or image or video prediction. So there's just many fewer methods out there. They actually had the bravery of submitting this without any comparison, right? So if you look in the reviews, the reviewers already accepted the paper.
That's good.
Well, they didn't even have this comparison to what's it called, the FiNet,
The VNet or the 5-flow.
five flow. They didn't even have five flow in the initial submission.
Mhm.
So yeah, I mean, it's a little, it's tough to think what else would you compare though to. I mean, because there's plenty of ways of solving incompressible Navier Stokes, but they're saying we want it to be differentiable and we want it to be unsupervised.
Mhm.
We're not requiring numerical integrations as training data, so we're not limited by the accuracy or speed of some existing solver. So I'm thinking
Yeah.
the one thing they could have compared to perhaps is physics-informed neural networks. But even there, I mean, I think they mention, I think quite conspicuously in a few places, that well, that's all very nice. They can do great things, but right now there's no way of training those to work with more than one initial or boundary condition. So I think it's a pretty empty field right now.
Oh, so you're saying basically they were the only so yeah, I guess my question really is whether, there's all these physics informed neural networks papers out there, and it seems like it's quite a lot, as in around 50 or more. And many of them target slightly different fluid problems or slightly different fluid problem setups. And I wonder whether it would make sense to sort of say, okay, here's one fluid problem setup, and that should be targeted if one is to propose a new physics-informed neural network solution.
I agree. This is another point that came up in the reviews actually, and in the in their responses, I think they do say, I don't know if I'll find it in 1 second, but they say, look, there aren't great benchmarks. We need to define basically, these simple cases. But I agree that they're different. They're not all different papers are using different things for evaluation, partly because they're trying to do different things. And I think exactly some kind of standards or benchmarking would be really good to have.
Mhm.
And I think it is. I think it's also inevitable, right? When you have these kind of new subfields emerging, then I think for a while everybody will do their own thing, ensure that they're best at their own task, and then eventually someone will say, "Okay, let's compare this systematically."
Yeah.
Yeah. I do think the being able to handle new initial conditions is quite big, and I think being able to start off in the middle of some other simulation anywhere, is really, really, really cool. So I think
That's
this is really something new. Yeah.
Agreed.
If I may quickly chime in on this,
Hmm.
I do agree that the results section is a bit thin. And there's two things. First of all, the comparisons, there's not that many, as is already pointed out. In fact, I think the only numerical quantitative comparison against anything else is on this table 1. There's one number, essentially just the LB, right? The divergence loss. And it's very nice to see that the divergence loss being true to the divergence loss being baked into the network also shows in the final results. I mean, that is very nice. But they could have, if I'm understanding this correctly, they could have compared with a classical numerical solver, right? You just start all the methods from the same initial condition and then you just check how this works with a non-deep learning solver, right?
You're actually right, and they could have even done this for Phi-flow, which even though it's differentiable, it's still a numerical solver.
And the other thing that is weirdly lacking from the results section is just the whole temporal aspect. Like most of the results, except for figure 4, and I think one in the supplement, they're just on snapshots, right? One state at one given time point, but the whole thing is about dynamics and rolling them out.
Well, the LD and LP do depend on pairs of adjacent in time states, right?
Yes. But that doesn't necessarily mean that errors don't accumulate at different speeds over longer rollout times. Like just starting their method, and I'm not saying that the method can't do it, I'm just saying it's not shown and it's a bit weird.
I think you're right.
Method from not just some random 0 velocity state as they do, and then they have this burn-in phase of some 70 to 100 steps, which you see in figure 4. Just you start with a valid state of the system, which is realistic, and then you just look at the next 20 or 30 time steps and you compare that. Like how quickly does it diverge from a ground truth reference that you're happy with? This was something I'm kind of missing in this paper as well, actually. But otherwise, yeah, I mean, the idea and everything is very cool, especially the fact that you can train a fluid simulator without needing a reference simulator just from the equations. If you think about this, this is how you actually want to go about this. But yeah, I agree that some of the methods, the results section has been really a bit thin.
I think you're right. Now that you mention it, I'm actually getting very suspicious they don't show the direct comparison to numerical integration. It almost, yeah. Maybe there's some reason, some butterfly effect thing happening, but at least the low Reynolds numbers, it should match, right?
Maybe it was a lot of work to get this done for the specific setup, but I mean, a standard numerical solver should also be able to generalize to a lot of different initial condition and boundary shapes and stuff, right? Because it's just the equations baked into code.
Yeah.
Plus,
this is something I noticed.
Plus, maybe just to add on this, it seems like the whole point of the paper is also to come up with a faster differentiable solver. So I guess if you would compare against standard numerical solver, it would be great to see that improvement in the computing time.
Yeah, that's
Or not.
true. I mean, they're kind of hiding behind the differentiability thing, right? And saying, well, compare to Phi-flow, which is differentiable. But no, but you're right. I mean, if you only cared about speed and you weren't going to put this into an optimization problem, then exactly you could use plenty of other solvers, which probably would be faster than Phi-flow.
Right.
Yeah, this is a good point. There's one more point I would make, which I find kind of interesting. It's not exactly a criticism, but it's, I think, worth mentioning. Just go back to my slides. So this U-Net structure, right? We've got 3x3 convolutions. So how many neighboring pixels does each output depend on? Well, it's a bit tricky to compute just looking at it because there's different resolutions, but you know, we have we have basically 5 by 5 over here. Then we drop down a level, and then we have an additional 2 on each side for each step, because now we've cut the resolution in half. So that's, we have on each side, we have 2 neighbors, plus 4 neighbors, plus 8 neighbors, plus 16 neighbors, plus 32 neighbors. So I don't know, off the top of my head, we're talking, and then we have to go back up. We're talking about maybe 100 pixels in either direction, so not quite the full space. This is probably fine, but maybe not completely, right? Like if you compare to a, so the point is, I'm emphasizing is, if I look at one of these solutions, if I look at 1 pixel here, and if I want to calculate the pressure and velocity field in the next time step, how far of a distance in the input does it depend on in the current time steps data? And there's a limit, right, with this architecture. It doesn't go on forever. Whereas if you look at the numerical integration step, right, when you do these decompositions, the Helmholtz decomposition requires solving a large linear system for which every output of that solve operation will depend on every input. So information travels throughout the entire solution space. Now, okay, this is part of the reason why this can be slow, because you're solving a very large linear system where every input can affect every output. But it also means that it's not possible for this unit architecture to perfectly imitate the numerical integration, because it simply doesn't have access to all the information going in. And this may not be a big deal for these sizes when we're talking about maybe 300 pixels in one direction. And of course, depending on the pressure gradients and the velocity fields, the actual practical effect of very distant locations in the next time step might be very small. But if we make the resolution higher, I don't just mean more pixels, but basically if we make the physical distance of these pixels smaller, then at some point we're going to need to increase the depth of our network or the size of our convolutional filters in order to get accurate solutions. So they're very fast because they only require a feed forward pass. And but at some point this actually does become a limitation. Is my view on this. Yeah. Any other questions, comments? Go ahead.
Just maybe one, and that is regarding the training regimen, which is, again, it's very cool that you don't need any simulation data. You essentially just work with the equations and being consistent with them. But one thing that really caught my attention was some of the wording in the segments that were describing how, I think, every other time step or something they called it, they replace some of the training points in the pool with some others. So I was just wondering how fiddly that is to set up, because you get interesting dynamics when your data set depends on the current state of your network, and then the next state of the network depends on that data set again.
I'm not sure I fully understood. You're saying, so, I mean, you're talking about the bottom paragraph here on the right? Marcel? The connection seems to have failed. Can anyone else hear me?
Yes, I can hear
Yeah,
you.
sorry, I was just gone. I was just
Okay.
gone for a second.
I thought they might have something to do with the hailstones and thunder, which have just started here in Bergedorf.
Yeah, as you said already, it's interesting weather today. We just had a hailstorm, small hail. No, so what I was asking myself is how fiddly is it to get the training done? So you start out with this initial pool of states from which you want to predict the next state. And then there seem to be a bunch of hyperparameters involved, like the rate at which you replace them, and the rate at which you randomly introduce new initial states from which this process seems to start. They have this thing in the supplementary material where they show what happens if they don't get this right. I think
Yeah.
figure 11 or something. I was
Yes.
just wondering if it's very tricky, because we know, for instance, from I think classical case is GAN training, where you also have the thing that some of your training data depends on the current state of the network, because it's generated by this generative part of the GAN, and then you get all weird effects like mode collapse that I guess in this case it would maybe collapse on certain states that have zero velocity or something, because then the next state would pretty much be the same again. I'm just curious, based on the wording in the text, how difficult this is actually to get to run them.
There could be several things happening here. I mean, so Kubi, this figure 11a might seem familiar to you. This looks a lot like the, to me, the training curve for pins when you don't do their hyperparameter fiddling properly and use the right training procedures. But
Yeah, exactly. And also they have these weights, right? These weights for the different losses, and I think they also have a strong effect. They mentioned that they, depending on which parameter you use, you also don't see specific physical effects or such. And then there's also the question of how dense is your time sampling and stuff like that. So you always have some kind of filter of processes, right?
Yeah.
Implicitly.
But I'm curious a little bit about what's happening in these error spikes in figure 11. You know, for whatever reason, it's failing, but perhaps it's not totally clear to me why. There's also something a bit mentally challenging to me about, okay, it makes sense if your network is working really well, then you're generating all these new states. You start from zero velocity and pressure. It quickly develops because of the velocity of the boundaries and so on. It'll develop into a realistic looking fluid dynamics simulation. But if your network isn't good, if it's violating its own boundary conditions and its own differential equations, then using that weird errorful state to feed back in to generate more training data seems a little strange. And maybe this is why they have to do resets. But I'd like to know what do those simulations actually look like in those error spikes. I'm really not sure. Yeah. Well, we've criticized this a lot, which is weird because I think universally it's pretty positive, everyone's reaction. I think it's a great paper. But yeah, there's definitely some practical questions, and I guess those will be resolved. Maybe they already addressed them in the 3D paper. I haven't really had a very close look.
Yeah, sorry, also from my side. I really like the paper. Also how it's written and how it's introducing its concepts.
Yes. Yeah, this is a very nicely written paper. Yeah.
There was another question about the Helmholtz decomposition in chat.
Mm-hmm. Yeah. Oh, I have not seen the chat. I'm sorry. Let's open the chat. One moment. I'm sorry. Maybe someone else can read it.
I can also ask it directly.
Yeah.
I was wondering, since the Helmholtz decomposition shows up in various places and various well-established numerical approaches exist, if there is any work where neural network approaches are compared to these established numerical approaches explicitly for the Helmholtz decomposition, not in a fluid dynamic setting?
I don't know, but I think the Turi paper, which I mentioned and which these guys also mentioned, would be a good place to start. But I honestly don't know.
Okay, thanks. I will check it out.
So, I mean, you're talking about. So the neural network never did the Helmholtz decomposition, but rather they just, they used the Helmholtz theorem to output a divergence flow velocity field.
A neural network that does the Helmholtz decomposition.
That I don't know of. Maybe anyone else can chime in. There are, I mean, more generally, there are papers, Marcel, you might remember this. I can't remember from which group, but where they use a neural network in a fluid dynamics solver where they didn't try to replace a numerical solver, but rather the neural network simply gave it a good initial condition for solving something either like an implicit step or a Helmholtz decomposition or a Poisson equation. I don't know if you remember what I'm talking about, Marcel.
Not at the moment, but just to get the question right, you're asking essentially if we look at the equation that David has right now on the bottom right of the screen, you're asking for a network that essentially takes the velocity field v and directly outputs the corrected, like.
Yeah, I mean, if we look in the paper, they give the slightly more. So when you actually want to do this, what you're actually solving is this problem here. You take the gradient of the, you take the divergence of the vector field, and that should be set equal to the Laplacian of Q. This is what you want to solve. And basically, you can think of this Laplacian in the discrete case as basically a 3x3 convolutional filter. So we're trying to find, so this is now, we take our velocity field, we calculate the divergence, so now we have an image, a divergence image. And now we want to basically say Q is our unknown image, divergence of the velocity field is our known image, and we want to find our Q such that when we convolve it with our 3x3 filter, we get the current divergence of the velocity field. And this is our Poisson problem.
Okay.
In fact, you can, it's done in different ways, but if you have a regular grid in space, you can actually do this in Fourier space very efficiently, right? Because then this convolution becomes multiplication in frequency space. So then you basically would take the FFT of this, divide by the FFT of your 3x3 filter, and then take an inverse transform and you get Q. But even that is still much, much, much slower than doing a forward pass through a ConvNet.
Yeah.
Cool. Any other questions before we close? All right. If anyone has any suggestions for future papers, Carolina, I like the idea of trying to find a case where the neural network is actually solving the equations inside a solver. I think we might be able to find this, and this might be a nice topic for the future. But anyone else with suggestions, send them along. If you like to present your work for 5 minutes or make an announcement, let us know. And so thanks a lot, and see you all in 2 weeks.
Thank you for the presentation.
Thanks.